manufacturer actually has software written that you plug our microphones into their board, our computer program pops up on their control screen, and you control everything from their console, which is really cool. Sound devices, which is a remote, they make remote recording devices like field recording. They have AES-42 inputs. It's becoming more and more popular just recently, actually, which is nice. The manufacturers are starting to see the benefits of it, and they're starting to see that people are asking for it, especially broadcasters, which is what we've been pushing forever and ever and ever. So, and this can get a little confusing, but our stuff, you know, our stuff operates on mode 2. There's a couple of different modes. So the now is there's no weirdness going on.
Like a big Ben digital
like
clock.
Exactly.
Okay.
So ours will lock up to a Big Ben or a whatever, an Apogee, something or other. When I do small demos, I have a little M box I bring with me, and I lock up to my M box, and it's easy. Right. Or our mics can also be the sample rate master and can generate the clock, and you can slave to our microphones, whatever. Everybody else, and I mean everybody else, runs on mode 1. Why, I have no idea. Mode 1 products basically means they can't lock to external. They have to have sample rate converters in their product for sample rate, which doesn't sound like a bad thing, but it adds cost, it adds latency, and it doesn't affect the sound quality. So we think mode 2 is the way to go. Most of the manufacturers think, well, mode 1 is easier, let's do mode 1, just so you know what the difference is. So some of our products, we plug our products from mode 2 directly into an AES-42 product that only works on mode 1. You'll get audio, it'll pass audio, it'll work fine. You just can't remotely control it. It won't talk to our software line to talk like that, have my laptop or a laptop plug-in running on software. Not that it's that big of a deal, but just so you know, there's kind of a difference in how we make AES-42 stuff and how some other people make AES-42 stuff. And then it gets very whatever. So one of the things you can do, especially for live stuff, is all of a sudden you had 90 channels of digital audio running down Cat 5 cable. So at the front of house, I mean at the stage, you have all these digital microphones plugged into a couple of boxes. Out of those boxes comes the Cat 5 cable, and then another Cat 5 for redundancy in case one of them happens to break. 90 channels on this little which is awesome. You know, this big massive snake shaft and big stage boxes and all that copper and stuff. Right. In theory, you don't have to do that anymore. Yeah, basically, if you wanted to do that. And this is the back of an Anovus. This is an Anovason console. This is a French manufacturer that allows, they're the ones that can control our microphones from their board. But just so you can see, you know, when you deal with fully digital stuff and digital PA systems, it can be as cool as this and as simple as this if you want to go that route. I'm actually going to be in Minnesota next week doing a bunch of recordings with a 64-channel digital system. So 64 channels over MADI, if you guys know what MADI is at all. It's
some of them
digital,
know.
Yeah. It's over like a little
fiber optic,
like a coax cable. Yeah. So 64 channels going over coax. You know, for us to record, it's awesome.
You still have 64 faders, or is it just compacted into one?
No, 64 faders. In this case, they all come up on a computer screen, and if not, I would have my laptop and page through 64 faders. Yeah. So you have 60 control of individually of all of them. Yeah. And then you can save the settings in the microphones, which is why we can talk to the microphones back and forth. You can actually set up a whole show, save the settings, tear everything down, come back the next week for the exact same band, the exact same show, boot them back up again. In theory, everything's identical. All the gain, compressors, everything is saved, which is really cool if that's what you want to do.
So are they daisy chained with like just one cable? Or?
Yeah, basically. Yep. And I'll show you some of the converter boxes later, but I have some pictures of them actually.
You can send power on that kind of cable?
Yeah. Yep.
Kind of wild, right?
Yeah.
So, digital microphones are I keep saying it's a sonic picture of what you hear. It is the exact thing that's happening in the studio. And the one comment I get a lot when I do digital demos is it sounds like the person's in the room with us. That's what people, it's very kind of 3D sounding. It's not 3D, that's a stupid way to put it, but I don't know how else to describe it. It's very realistic, let's put it that way. It's like realism. And I've sent, I work with the guy that does all this hip hop stuff with me at home. And I sent him a jazz track I did and say, listen to this girl's voice. I thought it was a cool singer. Didn't tell him what the microphone was, or she was recorded on a digital mic. I just liked how she sang. He emailed me back and he said, man, it sounds awesome. It sounds like she's in the room with me. And he didn't know what I used, and it's because I was using a digital mic. It almost like jumped out of the speaker. It's hard to describe it. Yeah, you'll hear it later. But anyways, some of the advantages. No noise. There is no noise floor in a digital microphone. Noise floor is molecular thermal noise, which is way smarter than I don't even understand it. That's way above my head. So when you start talking about molecular noise, you lost me, and that's where we're at. You know, normal, good, quiet microphones have a super low noise floor. You put them in a studio, you don't hear the microphone. You might hear the preamp, and you might hear the air conditioning from the room, but you don't hear the mic. These are way below that. There's nothing to hear. Like, you plug these things in, and we'll probably see later, you don't know if they're even working until you really start cranking. You got to crank them level way up, and all of a sudden then you hear the room. You don't even hear normally you plug a mic into the preamp, you hear the noise of something, a cable, a mic pre. These you don't hear anything. So no noise, no harmonic distortion, a very wide dynamic range. And I have a graph of that. I'll explain that later. And it's the most ideal way to transform whatever you're recording into your computer, basically, without gumming it up with anything in the middle. Woo, look at that. I'm going to do that again. I can't take credit for that because I did not do that.
I don't even have it. So dynamic range, just to give you guys an idea of what I'm talking about. So the old days analog tape, a big dynamic range of 75 dB. Dynamic range is the whole signal that you're looking at. Here's our U47, you know, these are old microphones. They all came out and their dynamic range was bigger than what they're recording on. Like you saw a big range like this, they put it down on a tape like this. So that's what was happening. All of a sudden, we did digital TV first that just came out. Like back then, we're quite up to dynamic range. And all of a sudden, we started to say, you know, that's very important.
So we're looking at 144 dB dynamic range. We have a converter in the microphones that gives you 140 dB dynamic range. So we are almost as max as we can possibly be. The only thing that holds us back is the capsules. The capsules are still analog capsules. Now the capsule in that first big fat mic, I had a picture up there, the DO1, that's a brand new, it's its own design capsule. It's not an analog, something that was just stuck into a digital body. It gives us 135 dB, but we're held back by that capsule, by capsule design. So the converter can actually do more dynamic range. So basically, it's as close as you're ever going to get to realizing the maximum capacity of your computer. You know, 192K sampling rate, whatever. Digital microphones are as close as you're ever going to get to it. And that's why they sound more realistic, because all of a sudden more harmonics come out at you. You start hearing stuff that you couldn't hear on analog mics because they just can't reproduce them, period. Ours or anybody else's, you know. And again, not that that's good or bad, it's just different. You may not want to hear some of that stuff. You may be recording in a bad room, and all of a sudden these digital mics tell you, man, all I hear is air conditioner noise. Whereas when I was using analog mics, it wouldn't record that because the noise floor of the mic was above the air conditioner noise. And I kind of canceled it out. Now all of a sudden the digital mic tells me that room sounds like crap. and it happens. But does that make sense? Because this is the big key to it, is this dynamic range thing and our converter and how we can get almost to the max, basically. And eventually we're going to get there, or somebody's going to get there. I think it's going to be us. That's just me. So. So, this is stuff I could talk about. Yeah, this is stuff I already talked about. This is more about the converter, but basically what it's saying is we didn't like anybody's converter because we're Neumann and we can do that type of stuff because they're very strange there at the Neumann factory. But so they made their own, which is cool. They tried on everybody else's stuff. It didn't quite get them basically the dynamic range they wanted. And most, I should say, all converters that are made now are made pretty much the same way. Our converter was made differently. The engineers found what they thought was a better way to do it. So, and I have pictures of it. Basically, there are two converters in our A to D converter. And other people do the same thing. But you have to have some way to switch between these two converters. And when you switch, when certain signals go to one converter, certain signals go to another converter, you get switching noise. And it could be theoretical, but there's always some kind of noise in the signal path with the switching. Neumann decided to figure out a way to do it without incurring any kind of noise whatsoever. So they made their own. And I'm going to go through this because this will make your head spin. But let's get through this. Okay, there we go. So this is a normal A to D converter from anybody. Any company, this is how it's made. Signal comes in, goes to a couple of different amplifiers. Here's first converter, second converter, and these are all on like a little circuit board, usually a little tiny chip. And then here's a DSP box that kind of switches between which signal they want, and there's a little switching, this little thing that switches back and forth. That switching noise, or that switch, can cause noise. And it could be audible noise, it could be, depending on how the DSP written, it might be inaudible, but there has to be a lot of DSP written on the back end to make you not hear this switch, right? Which involves latency and resources, basically. And it can never be silent. It will never, ever theoretically be silent. And this is kind of shows you, here's where they switch, right? Here's where the A to D converters switch, these little marks right here. This is where you hear that noise. And it results in high frequency glitches. That, again, you may not hear, but it's in there. So this is what Neumann did. Very similar. Here's our A to D converter, and here's the first one, here's the second one. They did it differently where there is no switching. They kind of employed a noise gate, and there's no hard switching from one to the other. There's kind of a blending. It'll take me forever to explain it, but let's put it, if you guys want to read it, I have like a 40-page white paper that you can read about it and put you right to sleep. Believe me, it took me forever to try to get through it because I am not a DSP engineer. So it results, there we go. It results in this, a much smoother output. And these are measurements. This is not a picture we just made up. These are actual measurements. It results in a smoother output, the switching. You don't have these little glitches here switching between converters. There's a nice smooth line. That's why we made the converter the way we made it. And it gives us more resolution. It gives us more headroom, but more dynamic range. And again, you can read on and on about this if you really feel like it. So, you guys, have anybody used USB microphones? You guys have them or have used them? Yeah, I mean, it's a totally different beast. It's not made anywhere like what this thing is made. USB mics are cool and they're good for quick stuff and podcasting and getting an idea down. Not the most high fidelity. That's not what they're made for. They're also very inexpensive, whereas these are not inexpensive. But that's a totally different ballgame. We'll never do a USB mic because that's not what we do. USB standards are very limiting, dynamic range-wise, and noise, and powering, and other kinds of stuff. So, but we made up the first system according to the first microphone system according to the AES-42 standard. We're hoping